So I'm presenting my work on reinforcement learning for intrusion response in network security. So a little bit about me and the sort of what went on with my placement. So I am Matthew Rini. I'm going into my third year of my PhD as part of the Cyber AI Hub in CSIT, which is Queen's University Belfast down in the Titanic Quarter. And my partner with this research was BT, British Telecoms. So we had identified a while ago at a SPRITE Plus event, we had quite a good overlap with our projects. We basically just have sort of different application areas. And I got to head over for a month, May, June time, to Adastral Park in Ipswich, which is southeast England, just sort of an hour from London. So the weather was a nice change for me. It's a bit wet and miserable in Northern Ireland most of the time. So to discuss the sort of problem we're looking at, network security, with the increasing complexity and size of networks, it's becoming essential that we develop sort of autonomous tools and techniques to respond to the sophisticated and potentially automated attacks that are rolling out. And ideally, we want these to be quick so that they can minimize damage and losses. So my sort of research looks at this at a cyber physical sort of IT OT point of view. I work on a testbed environment which is based on like an aircraft network, and it's to do with aircraft engines. So my sort of need for fast response is, preventing communication loss within the engine, whereas BT are looking at the same problem, but on a much larger scale, with things like corporate networks, whereas mine is about 10 computer nodes. They could have tens of nodes or hundreds of nodes, and so they have a much bigger problem, but a very clear overlap. So because of that, the solution to this problem using reinforcement learning is fairly applicable to both. So over on the I don't know if I can get a laser pointer. Yep. Over on this side we have the environment, and I said both of ours differ, but within that we both have an adversary, and then we'll have a defense agent. So this defense agent part works mostly the same, even if you change the environment or the adversary. So it takes in state and reward information, and the states reflect the status in the environment, and the reward quantifies those. So if something is bad, like a computer gets turned off, that'll be negatively penalized in the reward, and if good things happen, it gets positively rewarded, vice versa. So when it takes in these states and then quantifies them with the reward, it's looking to optimize to get a high as reward as possible, and it does this through a deep neural network, and it forms a policy that says, right, you should take this action within the environment to maximize your reward. But within that, there's obviously a lot of places for nuance, and it's sort of an up-and-coming area of study. So within my placement, I sort of looked at a number of activities. So I did a lot of sort of knowledge exchange and building of relationships. So I was sort of presenting my work and the intricacies of the things that I was interested in. And I got a very good look at the sort of different projects that BT were working on and that were trying to sort of actually take to market. And their team was like, we're trying to get these things, put on real networks to test them and see, is this going to be a viable solution in the real world for their customers. So it's very interesting to see how they're taking research to industry. We had agreed on a number of topics for literature review. I'll go into those later. From this and the work that I conducted in the sort of differences between our approaches, I was able to come up with a number of new research ideas for BT to potentially take away and work with, and also for my own PhD work and thesis. Lastly was some hands-on experience with their simulation environment, which is very different from my emulation. So moving on to literature review, the top three topics that I looked at was co-evolutionary games for network security. This is looking at not only having an AI-driven defense solution, but an AI-driven adversarial solution. And the idea is that by training both of these, you're able to get a better defender if you have a very sophisticated attacker. Then looking at multi-agent reinforcement learning. So this is where you have multiple AI defenders or multiple AI attackers. This brings about a number of issues because these agents have to collaborate and can, in some instances, have clashing ideas or optimizations and can cause infighting. So there's a lot of work of trying to get agents to cooperate within the same space at the moment. How do you best do that? Do you separate up lots of small agents, or do you put a big area with many agents overcrossing? It's a big area of interest at the moment. And then looking at bridging this simulation to gap. So BT used a big sort of simulation environment, which is a very abstract training environment, and they want to bring it closer to a real system so that they could eventually deploy it. The in-between step is sort of emulation, and that's what I'm looking at. So it's trying to see, like, what are the reasons why you would emulate? Can you have those in simulation, or how would you get from simulation to an emulation stage? And then beyond that, looking at, well, how would you go to deploy it to a real system? And there's a number of things, not in cybersecurity, but in the robotics and automotive industry, that are sort of creating timelines for these tools and sort of processes to get them to the consumer or deploy them onto real systems. Some other areas I looked into, action masking. This is whenever you deliberately tell an AI which actions it can or can't take rather than it just learning. And this can be important if you know that these are invalid due to a particular set of constraints that you don't want to take the time to teach it. You can just basically tell it, you might want to select that, but we're just going to say that's an invalid one, and it'll choose like the next highest probability. Investigating synchronicity or simultaneity of the defender and attacker. My system, they both run at the same time, like two teams in a football match, and they can move whenever they want or simultaneously. The BT system works sort of a synchronous matter, so the defender goes and then the attacker goes, more like a game of chess. And what sort of different outcomes do you have from training in these two different ways? And then looking at static versus dynamic action or reward costs, and that's all to do with how you form your or penalize your reward. Should you basically have set assumptions, or should this purely be based on the values coming out of the environment itself? I came up with a number of research ideas for BT. So red agents, blue agents, so that's adversary profiles. Blue agents is on the defense side. Green gray agents are like benign users. We collect a lot of data. Could we use this in a way to do offline learning with like traditional machine learning techniques? Differences in the computational speeds of the adversary and the defender. How does that change training? In the experimentation, I basically began to implement the first of the ideas that I produced for BT. and had some promising results. I can't show any of that stuff here because of various IP stuff, but yeah, to sort of summarize the outcomes, I helped build relationships, and we have strong overlap, so we're hoping that we could potentially propose projects together in the future and get funding for these and work together. And I created for them a large sort of technical report with everything that I covered today, but in a lot more detail for them. So I'll leave my socials here if you want to look at my research or get in touch with me, and I'll take any questions.